This will be a brief introduction to COMSIM's KEEL Technology, or Knowledge-Enhanced Electronic Logic. First, the problem. There is a demand to do more with less, more intelligent force, more precision, more adaptive/reactive systems, reduction in human error, and at the same time providing these services at a lower overall cost. There is a small video that will be running in the lower right corner of the screen throughout this presentation. I will tell you what is going on a little later. The solution means that more functions need to be automated, which ties into the entire discussion of autonomous systems. You automate to increase speed, amplify power, increase quality, keep humans out of harm's way, to mass produce capabilities, and to deliver more value at a lower cost. So one approach might be to do more of the same. You go to a company with lots of smart people, and pay them lots of money to do all the work. More work equals more money. Infinite work means infinite cost. At one time in the past, the thought was that the telephone company would have to hire almost everyone in the country to operate the telephone switchboards. Another approach is to use artificial neural nets with genetic algorithms. This approach attempts to work like the human brain, using pattern matching to determine behavior. But I would suggest we don't want to make artificial humans that have the potential to learn bad things, and can never explain exactly why they do what they do, and are difficult to fix. Mass-producing systems with human-like failings can lead to very bad results. Maybe a new approach needs to be considered. So we have the question as to why everything hasn't been automated today. I would suggest that it has been too difficult to model and automate human-like judgment and reasoning. Judgment and reasoning provide the services for humans to deliver their expertise. The conventional development process today might include first a domain expert developing a functional specification and handing it to a mathematician who prepares a formula. Once the formula is developed, it is handed off to a software engineer to code and debug. Then the model is then placed in some type of simulation for the original domain expert to review, to see if it works as desired. This is commonly an iterative process that may take many cycles to develop. Remember, we are talking about the problems that have been too costly and time-consuming to develop in the past. I might even suggest that the domain experts may not know exactly what they want to create when they start the process. This adds to the cost and complexity. I will add, until now. This slide looks at the human brain and uses the left brain right brain paradigm to discuss decision-making. Left brain functions provide services that have been addressed with digital computers since their inception. They provide sequential processing of rules. If, then, else logic. Judgment and reasoning are more visual. You consider the value of information. This is an analog process as you balance alternatives and consider how much effort to apply. You use judgment and reasoning when considering alternatives, like what is the best approach, and how to use enough force, but not too much. This is the point where I would like to suggest that you think about yourself as an autonomous system. Think about how you maneuvered yourself into the room. You walked around things and people. You choose where you would like to stand or sit. You observe your surroundings. You moved into the area, continually adjusting your path as others moved around. You may have adjusted your plan based on what you observed. Who was there? Who you wanted to be near and who you wanted to avoid? This simple process made significant use of your judgment and reasoning. And at this point I want to suggest that the ability to package judgment and reasoning into autonomous systems is what will cause a paradigm shift in almost every industry, including the military and advanced weapon systems. So what is KEEL technology? KEEL, or Knowledge-Enhanced Electronic Logic, is an umbrella term. It covers both a new way to process information that maps to the way that a human applies judgment and reasoning, and it includes a new way to capture, test, package, audit, and explain human-like judgment and reasoning. And it is easy to learn and apply, and easy enables doing more with less. Another way to look at KEEL technology is that it allows you to package tactics and strategies in the form of executable policies to command the behavior of autonomous systems. You have been developing tactics and strategies to be executed by human warriors for years. Now, with KEEL technology, you can develop tactics and strategies to be executed by autonomous systems. We differentiate a technology from a tool. A technology provides a way to solve a problem. A tool, in this case, includes the KEEL dynamic graphical language that facilitates the delivery of KEEL technology in the form of a KEEL cognitive engine. we suggest that it is easy for a domain expert to capture and test his or her expertise and deliver auto-generated working code to the software engineer for inclusion into the final product. This is accomplished without the cycle of translating concepts to formulas, formulas to code, and code to simulation, all before the concept can be tested. The interactive nature of the language allows the domain expert to test the policy before handing it off for inclusion in the final product. With this process we can greatly reduce the development cycle time. KEEL cognitive engines are automatically created from the design. They are effectively providing analog computer functionality that can run on today's microcontrollers. They operate as if you had packaged the information interpretation and behavioral skills of the expert. KEEL engines are software components that are easy to insert into any design. They are simple functions or class methods depending on the language that you want to use. What we have added to today's computerized solutions is the ability for the machines to adapt with a human-defined value system, so the systems can apply judgment and reasoning in the pursuit of assigned goals. They can operate autonomously, or in collaboration with humans and with other systems. A machine can have one or many KEEL engines organized as if you organized a team of human experts embedded in the machine. Now I would like to show you a small demonstration using KEEL technology. Here we have a simulation of two unmanned aerial vehicles. Each autonomous system has a KEEL engine with a policy that controls its behavior. Each has the same goal, to find and engage the target that is shown by the larger red circle on the screen. There are smaller red circles that indicate defensive sites that can shoot at and damage our autonomous systems. In this simulation, our autonomous systems cannot see the defensive sites until they are shot at, nor can they see the target until it is within range of its sensors. The policy controlling the behavior of the autonomous system also provides sense and avoid capabilities, which comes in handy for collision avoidance. In this example, the autonomous systems are generating their own random search patterns to locate the target. They can also be driven by clicking on the screen to set the next intermediate point. The KEEL-based policy directs the autonomous system to choose between several optional activities: to search for the target, to attack the target, to make an evasive maneuver, to avoid incoming surface-to-air missiles, to hide, or to return to home base. Each autonomous system is continuing to evaluate its situation, considering its fuel supply, its health, its weapon supply, nearby threats, and the target value, once the target is detected. If a worthy target is detected, the policy balances risk and reward to determine the optimal instant to fire its weapon. During this period, it continues to monitor for new threats and exercises its collision avoidance capabilities. When the target is located, the autonomous system attempts to find a safe way to attack the target. It may try several approaches to accomplish this task. In this case we have added the concept of frustration into the policy, so if the autonomous system cannot find a safe way to attack the target, after some number of attempts it will give up and try again another day. We have some canned scenarios in this simulation that allows us to replay some of the situations. We have also added a mission control adjustment to the battlefield management system. This allows us to change how the autonomous system interprets information. This way we can have some human control over the behavior of the system, and still allow the autonomous system to operate according to official rules of engagement. This is different from having a human operator exert full remote control. The autonomous system has more knowledge if it's real-time situation, and the remote human operator. It might be, however, that the remote operator has access to some intelligence not available to the autonomous system. So this approach allows new information to be integrated into the behavioral processing. In this policy, the mission control adjustment tells the autonomous system that the target is more important than the autonomous system thought it was, and that it was to be more risk-tolerant when evaluating its situation. This is a very simple example of the KEEL toolkit. The top bars are outputs, or actions. This design has 4 outputs. We have used the default names of Action 1, Action 2, Action 3 and Action 4. The bottom bars are inputs to the system. The ones with green caps are reasons to do something, and the ones with red caps are reasons not to do something, or blocking reasons. Note the purple diamonds at the bottom of each of the inputs. If you click on one of the diamonds, you'll see the name of that input and its value. Also note that the inputs are segregated. Inputs 0 to 5 are associated with Action 1. Inputs 6, 7, and 8 belong to Action 2. And so on. As soon as the designer, the subject matter expert, adds an action and an input, the system is live. This makes it easy for the SME to check out their design. If you move the sliders up and down, you will see the system think. Now I will explain the wires between the bars. First look at the output named Action 1. The dark blue area shows the amount of the action. At the bottom of Action 1 you will see the amount of blue, in percentage. Now if you click on the little blue up arrow with a circle around it to the left of the percentage box, you will see two red lines appear. The amount of Action 1 is controlling the importance level, height, of Action 2. This is the first wire. It is also controlling the position of the threshold in Action 3. Thresholds turn on and off outputs. In this case, the threshold is turning on and off Action 4. Now, if you click on the little blue up arrow with a circle around it under Action 2 you will see one red line appear. The amount of Action 2 is contributing to the resolution of Action 3. You can have an unlimited number of outputs and inputs, but in this case, Action 2's resolution is contributing to Action 3. Now I will show you how decisions are made. We will just be looking at Action 1. First we will drag all of the inputs down to 0, so there is 0 reason to do Action 1. Now we choose either input 0, 1, or 2, the sequential order doesn't matter. Left-click 5 times in the white area of that input slider. You will see that there is a 50% reason to do Action 1. Now I will click 5 times in another supporting input. Adding 50% of the remainder is 75. When I click 5 times in the last input, you will see that the result is 87.5, adding another 50% of the remainder. Now click 5 times on one of the red or blocking inputs. You are taking away 50% of the value you had accumulated, which leaves 43.75. Click 5 times on another blocking input, and the result is 21.88. This is the law of diminishing return. It will never go below 0, or above 100%. Now drag one of the red, blocking, inputs all the way up to 100%. This is an emergency stop, or law of nature. This is when something is impossible. No matter how many 100% reasons there are to do something, one 100% reason not to do it will turn Action 1 off. Now briefly I want to touch on thinking in curves. In the real world, information influences behavior. This means that information bends curves. Here's an example of a time utility function that can be used to define the optimal time to make a decision. There is no value in making a decision early. Then the value increases to an optimal value, and then drops off quickly. New information can change the shape of that curve. With KEEL we can show how information can bend the curve. This is what happened in our first demonstration, with the mission control adjustment. Now I mentioned that there was a small video running in the lower right corner of the screen when I started. I don't expect you have been able to see it clearly, but during the 12 minutes and 24 seconds of the video, an engagement policy for an autonomous system was developed from concept through certified code. There was even a second iteration of the policy that added a new factor. So again the focus is on rapid deployment of policies that control the behavior of autonomous systems, telling them how to think rather than how to solve specific problems. I would like to invite you to visit us at the CompSim table and ask more questions and get a more in-depth introduction.